Now let's get started with the semantic segmentation. Okay, so this is the easiest. As I said, the objective of semantic segmentation is to segment all the objects, but they don't distinguish intra objects. Like if there are persons, multiple persons, they all will be segmented as one segment. Okay, so similarly, if there are multiple cats, they all will be segmented as one segment. So that's semantic segmentation. So let's try to attack this problem. So how to go about it? A very naive approach similar to what we tried out in the object detection is to move a window, right? And each of those windows you crop and then pass it through a CNN classifier and classify whatever is you feel like inside the object. So I'll tell with an example. So let's say you start with this section, you crop that out and you see that is a tree. So your CNN classifier is going to predict it as tree, and let's give a color to it for easy representation as pink. Okay, and in typical case you give a number to it. Let's say tree is number 1. Okay, the pixel, all the pixels belonging to tree should be in the mask should be considered as equivalent to number 1. Okay, so just giving an example. So you have to move this window all throughout, and let's say you arrived here and this is a crop from cow, so your CNN classifier will classify it as cow and you may give a number to it, let's say 2 or something like that. Okay, so you repeat this, you move window all throughout each of these you will sender, so you'll have literally a classification for each of these pixels in the image. So you move this similar to a convolution operation. Okay, but each of these crops you need to use the classifier, so that's similar to the RCNN where you had region proposals, and each of those region proposals you needed to pass it through a CNN classifier plus bounding box regression, right? So here just a classifier only, but you need to literally move it throughout. And let's say the last one, so you have here it's a grass, so it predicts as grass, and let's assign green color to it and maybe a different number to it. So after you repeat for each and every pixel in the image, you literally can combine them and you feel like a segmentation mask here with different colors. So this is semantic segmentation. All the cows are considered as one, brown in this case, and similarly other background regions or other objects are having a different color or different number to it. Okay, so this is a very trivial approach and this is easy to implement. Actually, there's no problem, but the issues here is of course the size of the window. You have to fix it, and that's an uncertain thing, and it's highly complex because each of these crops you need to pass it through a CNN classifier. So that's something which is not good, and it's redundant also, right? Because if you move the window by, let's say, stride of 1, the trees may be overlapping too much, and that's like overkill of computation, right? So it's not something which we'll always prefer. Okay, we need to have a better approach, and that's where the first convolution kind of or fully convolutional kind of network came into existence. And you can see here this is quite straightforward. So what you do is you take the input image, pass it through a layer of convolutional layers, I mean series of convolutional layers. But one important thing, you are not doing any strided convolution or max pooling here. So literally you are not reducing the resolution of the image here. Okay, so no change in resolution, right? It's throughout h cross w throughout. Okay, d cross h cross w, h cross w, see everything is h cross w, or you can say no scaling. Okay, so it is basically having kind of a linear receptive field. It's really not looking at the images at multiple scales like we typically do in a classifier encoder, all right, or in an object detection encoder where you kind of see the images at multiple resolutions. That's not happening here. And you see a particular thing at the output, the final layer will have this size. H cross W is of course all the pixels, and for each pixel you have a class, right? So the see here, the channels here is the class of the pixel in that sense. So this basically makes sense. It is in line with something like YOLO where we had that last layer as a 3D layer, right? So here also it's like a 3D layer, but it just represents all the pixels and class for each of those pixels. Okay, and then of course if you consider the max value for each of the class, you can assign the particular class to that pixel, right? So that's the idea. But the problem here, as I said, since the network is not seeing the images at multiple scale or the receptive field is linear, the convolution is kind of redundant because all the layers are seeing the images at the same resolution or the feature maps at the same resolution. So it's really difficult for this network to perform robust because smaller objects may be missed sometimes. So various issues are there, right? And also it's not a perfect design, you can see from here. So we can only improvise from here. and that's where the different aspects came, and I would like to go into those sophisticated models. But before that, as usual, let's make a quick detour, and this session will be dedicated to that. So that's something known as the losses in the segmentation. So image segmentation, just like the classifiers or the object detection, losses are extremely important because that is how you set up the back propagation, right? So don't forget that. So are similar to the object detection, where you had two kinds of losses. One is the classifier loss and the other one is bounding regression loss. For an image segmentation, you have two losses again. One is the classifier loss and the second one is the location loss, or some people call it as overlap loss. I think I'm also using this terminology in the demo, which I'll show you in a moment. Okay, so what is happening here? The classifier loss is exactly the same as we already know, and the location loss or overlap loss, some of them you already familiar with it, but I again reiterate them, and some of them are interesting to understand as well. So we'll start with a quick review of the classifier loss, and we typically has two types of loss. One is the cross entropy loss, which is defined by this expression where pt is p for y equal to 1 and 1 minus p otherwise. And we have the focal loss, which is basically this 1 minus pt raised to gamma by log pt, and when gamma equal to 0, this term vanishes, it becomes 1, and this goes to cross entropy. So you may be having some doubt here why this cross entropy expression looks bit different than what you have been using in the classifier. In fact, it is the same. Let me put the expression you might have been using earlier. So it will be something like yi log pi. Yi stands for the labels and pi stands for the predictions, of course softmax predictions, and then you have 1 minus yi log of 1 minus pi. Okay, and the sigma term I'm ignoring. This need I stands for samples, and you need to submit for all the samples, and if it's a multi-class, you need to submit for all the classes as well. But if you consider just this portion, it is exactly this. If you consider the entire thing, so if y equal to 1, if I put y equal to 1 in this expression, this becomes yi, so this becomes 0, 1 minus 1, so this entire term vanishes. Okay, I forgot the minus term here. Okay, so there's a minus term here. So this, if yi equal to 1, this entire term vanishes, and yi is 1 here, so minus log pi. That's exactly this. And if y is equal to 0, then this term vanishes, right? Because this and 1 minus 0 is 1, so this becomes 1, and minus log 1 minus pi, and that's again this. So this expression is an abstract representation of your already knowing cross entropy. It's not different. Okay. Okay, so just explaining it so that it's very clear to you. And now focal loss. If you see the focal loss here, we already discussed about this when we discussed about the RetinaNet paper, which was the one which introduced the focal loss, and this is something which is extremely useful when we have class imbalance problem. We discussed it briefly earlier, but I reiterate it here so that all of you know it again. So what is this? So if I plot this against the possible probabilities, so this focal loss against all the possible probabilities, so pt is changed from 0 to 1. So 1 is 100% confident, 0 is 0%, nothing, no confident at all. And for various values of gamma, so gamma equal to 0 is this blue curve, that is a cross entropy curve, and all others are increasing values of gamma. So gamma equal to 5 is very rare, gamma equal to 2 is what we typically use. Now let's understand why this should work. So let's say anything above 0.5, 50% probability is easy to predict, or that's highly confident prediction. So in the case of object detection or segmentation, these are kind of correlated with the background object. Okay, because background object is consistently present in all images, and that's the most common. So the network over time will be highly confident about the background losses. Now if you choose cross entropy, let's assume that we consider these regions which are above 0.5. Okay, so in the case of cross entropy, simple cross entropy, the blue curve, if you see the loss corresponding to 0.5 and above, it is still significant. It is above 0 and it is slightly below 1, so it is still significant. The back propagation works. Now takes this extreme case of green curve, this green curve, and anything above 0.5, this onwards, you see here the loss is 0. So that means there is no loss when the prediction or the probability is above 0.5, which means actually those highly easy cases or background cases, the loss function is forced to zero, which means they don't participate in the learning or the back propagation process. And that's exactly we want if there is a class imbalance, you should be very careful about the most common class that should not be used for learning a lot, because it will overfit to that, and our few cases or less cases will not learn that much. So focal loss is a way to force your classifier to learn the imbalance classes. Okay, so if you are not using it, you are losing that effect. So please try to use it in your projects, for example, which will definitely going to help. So let's move on. So this is all about classifier loss. So the total loss will be classifier loss plus the location loss. So what are the location loss that we can think of? Okay, so the first one is something which is borrowed from the object detection, which is some a loss based on the intersection over union. Okay, so we call it as intersection over union loss, or uh, it was proposed by a person named Jacquard, and hence its name is Jacquard loss. Okay, so what is intersection over union? This we discussed about in the object detection session. So it is ground truth intersection prediction divided by ground truth union prediction, and you can actually put it in terms of true positives and false positives. At this point it may be vague to you, but I'll explain this in detail with the help of um, uh, a diagram, so that it becomes very evident to you. Okay, so but before that, this is IOU score. So IOU score of 1 means your ground truth is, or your ground truth mask and your prediction mask are perfectly overlapping in the case of segmentation, right? So that's the idea. So if you want to use it as a loss, you should actually either do minus IOU, because loss you want to minimize, right? And IOU you don't want to minimize. IOU you want to maximize. So if you want to use it as a loss, you should either put a minus sign in plus of in front of your IOU, or you can do something like 1 minus IOU, because the maximum value for IOU is 1. So 1 minus IOU is a good candidate for minimization, right? So this is minus or 1 minus IOU is because you want to minimize a loss, and IOU per se is always you want to maximize, right? So that's why you put 1 minus IOU here. Now let me come back to this expression. How are you deriving it? So I'll explain this using a diagram here. So in this diagram, this green color region is the ground truth. Let's assume that it is the ground truth, this full circle, and this full orange circle is your prediction. So after the model is trained, it is predicting basically, or during the training it is predicting this orange region. Now you see there is an overlap, this part which I am shading as red. So that is the intersection part where the ground truth intersects with your prediction. Now that is the true positive, right? Because your prediction is saying positive, and your ground truth is also saying that is positive, so that's a true positive. Now this region in the ground truth which is not part of your prediction, that is false negative, right? Because your model is saying it is negative, it is not a segmentation mask, but the ground truth is actually there. So that means you are negative about it, your model is negatively predicting it, so that's why it's false negative, right? And similarly this part of the prediction which doesn't include or doesn't intersect with your ground truth, that's false positive, because it's not there. Your model is saying it's positive, but it's false because it is not in line with your ground truth. And whatever is remaining, the background, you can even consider it as true negative, right? Because that is not part of the ground truth, so definitely it is not positive, or it should not be there in the prediction, and your model is also not predicting that, so it is true negative. Okay, but we won't be using true negative, so you can actually ignore it. We only play with these three. Even for precision recall, if you remember, we only play with these three: true positive, false positive, and false negative, right? So this is the idea. And now you go back to here, the intersection over union, you know, it is the ratio of the intersection of your ground truth with prediction to the ground truth union prediction, right? Now what is ground truth intersection prediction? That is nothing but the true positive, because that's where both of them intersect, right? So you can put true positive here. And what is the union of it? That is basically all of them, right? So that is false positive plus true positive plus false negative. Okay, so the total, so that's the full prediction plus ground truth space you can think of. So this is a ratio of the true positives out of all the uh, possible space, which includes the ground truth as well as the prediction. So that's the idea. Okay, and the calculation is pretty simple. So you can how the IOU score calculated, basically you pass the predictions, maybe you do a thresholding, hard thresholding with some threshold, similar to what you used to do in during the object detection IOU calculation. And then intersection is nothing but the product. Once you threshold it, you essentially have kind of a binary scenario, and your target is already kind of a distribution which is uh, from their ground truth label mask. So in this case, because this is segmentation, I can just multiply them to find the intersection, right? Because this is a mask and this is also a mask, so multiplying them will give you the intersection. So that's what happening here. And then union is basically this same formula, but remember, you are adding this mask plus this mask, but then this true positive is counted twice, so you're subtracting that intersection one time, so that you kind of uh, have this formula. And then you can return this, but this is IOU score, not the IOU loss or the Jaccard loss. So if you want to calculate the loss, you just need to put 1 minus whatever value you are having here. So that's the idea. And now this is something which is very common. This loss is something which is very commonly used, and it directly optimizes the overlap ratio, right? The intersection divided by the total spread of your ground truth and prediction, right? So this is mostly used when you strictly want to increase the overlap. Okay, so if your objective is to go for maximum true positive, the IOU loss or the Jaccard loss is your friend. But the problem here is, if there are many tiny objects, the true positive may be very less, and then if you use this, you may not get a very good performance. So this is very important to note, tiny objects. So if you have tiny objects in your data set, maybe IOU loss or Jaccard loss is not your friend. Okay, so now let's move on to the next loss, which is something known as dice loss. So it was introduced by Sorensen and Dice, and hence the name dice loss. And there are two variations of it. One is with hard thresholding, the other one is with soft thresholding, and the soft dice loss is what typically used. Okay, so nobody uses the hard thresholding loss recently, but the equation is pretty simple. So dice coefficient was defined as 2 times the ground truth intersection, or the 2 times intersection divided by not union, the total sum of the two mass. So the difference is, there is a weightage of 2 here. The true positive is weighted by 2 in the numerator and in the denominator. This is not union, so you add the mask of your ground truth plus the mask of your prediction, so that's total sum, not the union. Okay, and the importance is, as you can see from the coefficient itself, there is more weightage on the true positive, and then this is coefficient to consider the, or you use it as a loss, you have to subtract it from 1 in line with the IOU score. So please remember that, don't just use the dice coefficient, because dice coefficient should be maximized, but dice loss is typically minimized, right? In optimization we minimize the loss. So to have that, you put a negative sign in front of the dice coefficient, or you subtract that it from the max possible value, which is 1. That is why 1 minus dice coefficient comes here. So this is important to note. Now what is the significance of this? I think it's easy to understand here. So this loss, let's say the there is lot of true positive here. Okay, so the true positive values are kind of dominating, so that means the value of dice coefficient will tend towards 1, right? So um, something like a background class, which is actually easy to predict. So true positives will be very high for those background classes, so that means the dice coefficient will almost approach 1, and then dice loss will be 1 minus almost 1, which is approaching 0. So that means this loss is also very useful in the case of what? In the case of class imbalance, or in the case of avoiding uh, over learning for the background classes, for example. So in the case of a segmentation problem where there is quite a lot of background class dominance, or the data set is heavily imbalanced, then this is your friend. The soft dice loss is your friend because of this overemphasis on true positive. If you consider the IOU score, the true positive was not overemphasized, right? So here you're overemphasizing it. That means there is a chance that you can use it for a class imbalance problem, and that's exactly why they propose this loss in comparison to the IOU loss, for example. Okay, and this is how they calculate it. So the top one is basically the hard threshold, where you kind of pass a threshold value and then you do the thresholding, and remaining is the same as similar to the IOU calculation, except that you are not subtracting the intersection again from here, because all you want is the total sum. Okay, and then of course if you want to use this as a loss, I think I should have kind of made it uniform, but no. you just need to do this, right? You need to subtract 1 minus from here. And then soft dice loss, you don't pass any threshold. You just use a sigmoid to kind of normalize everything to 0 to 1, and you use the raw prediction values, not the softmax converted values of your final layer. So that's one difference. And another difference is basically your denominator, you are basically doing a product. That's because you are kind of having, this is not thresholded, it's not a binary mask anymore, it has values in there. So that's why you are kind of consider this as a product of two values. So the denominator should also have the products, right? So that's why we have so kind of normalization with that respect. So that's the only difference, but the holistic picture that should be in your mind is this number 2 here, uh, in both cases. And this addition will also bring that number 2 times that. And because of that, the true positive is emphasized more, and because of that there is some relevance for this in cases where there is heavy class imbalance. So as I mentioned here, the true positive double weight is helping, and whenever you feel like there is too much of background in your data set, you can use this loss. You should not go for the IOU or the Jaccard loss. So a safe bet, just like people advise that for optimization you should use Adam optimization, for segmentation loss you should always include soft dice loss, because that's always better. Okay, and now last loss, but it's not definitely not the least loss that you should be understanding, which is known as the Tversky loss, or more precisely there is a focal version of the Tversky loss. Okay, and this is something interesting, and there is a specific application for this, but let me define what is Tversky loss. It's surprisingly same formula, but few manipulations here. Okay, so you have true positive divided by true positive plus alphas and beta weightage for your false positive and false negative. So explicitly what this loss offers you is some control on false positives and false negatives. You can explicitly control the number of false positives and false negatives in training. That's actually a critical factor. I think that's a really major innovation in the loss function in this scenario. Okay, so this is a very useful loss. So particularly in applications like medical data set where you can't afford to have false positive. For example, you go for a scan and there is a suspicious cancer tissue and you want to overrule that, and let's say your system developed as a false positive and giving you a positive for tumor, and actually tumor is not there. Imagine the situation. So healthcare situations or situations where safety or the false positives are critical, this is a very good loss actually. So you can weight your false positive here during the training. So that's a beauty. And similarly the false negatives also. So typically we go for beta greater than alpha, but we do give some weightage for both of them. Okay, so that's the idea. And then this is a coefficient, and the loss will be 1 minus Tversky, just like we discussed earlier. And there is a focal version of this, which is nothing but this entire thing raised to gamma. So gamma equal to 0, it converges to simple Tversky loss, but gamma greater than 1 is similar to the scenario where you can kind of penalize for the class imbalance and for very sparse or small objects. Okay, so small objects, focal Tversky loss is a friend of yours, because those are extremely rare cases and very difficult cases to detect. And if you remember the curve, the focal loss curve from the earlier chart, you can see that those are very low probability detection cases or segmentation cases, and they should be heavily involved in the training. So your loss will be very high and they will be involved in the training in a good sense. Okay, so this is a formula for the Tversky loss. It's quite straightforward. You calculate the true positives, false negative, and then of course this formula with weightage, you have hyperparameters alpha, beta, and gamma passed in from outside, and use that, and 1 minus this will be your loss. So it's quite easy. And where it is used, okay, so it is generalization of dice loss, because dice loss is basically the same formula except you have 2 times at the true positive, right? So you can actually literally achieve that if alpha equal to beta equal to 0.5, this becomes the dice loss. So this is a very generic formulation. So only you need is this particular function, and you can actually use the same for dice loss, or you can use it for Tversky loss or focal Tversky loss. Okay, so that's the beauty about it. So it's a generalized dice in that sense. Okay, and you have the tilt towards false positive or false negative here. And then if you add the focal loss, you can actually give emphasis to small structures, because they are very rarely occurring most probably, and they're very difficult to segment. So the probability of segmenting that is very less. So if you have the curves like in the previous slide, you can imagine the loss function is made more purposefully, right? So by doing that, you can focus on those specific cases in the training. So that's a beauty. So just to summarize, we discussed about a few losses. Of course, classifier loss is standard, it will be always there, but in addition to classifier loss, you always involve a localization or an overlap loss. So you have, of course, this particular guy, the focal Tversky loss, you have the dice loss, and you have the Jacquard loss. Okay, now let me just quickly show you a demo which you can play with in your free time and understand about the importance of these losses. So let me just go to that. Okay, so this is a demo I made actually. So uh, the binary and the multi-class segmentation option is there, but multi-class is not very useful, so you can ignore it. By binary, so we have all the losses here, so you can actually consider all the overlap loss or the location loss. So soft dice, IOU based loss, Tversky and focal Tversky here, and you can add or disable the binary cross entropy. Okay, so that's up to you. So we are not using focal loss here, but just the binary cross entropy. And then we have a ground truth two kind of circular structures here, and this is the prediction probability. So on the prediction part, you can shift your location. So let me just zoom out a bit. Okay, so if I kind of change it, you can see the object moving to the left and right, and similarly up and down also you can move. Okay, and then you have the radius of this also you can control. So this one is basically the control on the radius, so you can see it's expanding a bit up and down. And then you can add more blurriness to this by, if you reduce it to extreme 0, it becomes sharp, and if you increase it, it becomes kind of blurred. And there is a small circle or lesion here, you can actually disable that and enable that, because then the focal Tversky loss importance you can study by enabling and disabling this. And then coming to the settings here, so we are adding up the cross entropy plus the overlap loss, and that lambda, the weightage is basically given here. So lambda overlap will be the weightage for the overlap loss or the location loss, and lambda BCE will be the one which is given to the cross entropy. So if you're not using BCE, this value doesn't make any sense. So at this point, I'm giving 50% weightage, but you can play with it if you want. And then the hyperparameters for the Tversky loss and focal Tversky loss, like alpha, beta, gamma, they are all here. So you can play with all these. So if you are choosing soft dice here, these values have no meaning. Alpha, beta, gamma has no meaning. But let me choose the focal Tversky loss because that is the generic loss, and you can weight overlap and BCE here, and alpha, beta, gamma values, whatever you want to have. And you can see the losses at the end. The soft dice loss here, IOU loss here, Tversky loss here, focal Tversky loss here, and BCE loss here. And then whatever loss you selected, that will be displayed again here. And the total loss, the overlap loss plus the BCE will be displayed here as well. And if you want to see the parameter sweep, if you want to change the values of your probability and see, so let me just choose gamma here, and gamma is varied from 0. Let's say gamma 0 will be your Tversky loss, and gamma 1 or above, let me increase to 3, will be your thing. And you can see here the mixed loss, the total loss. Let me remove the binary entropy loss, so you don't need to do that. So you can see here, so these are the values of gamma. Okay, and you can see for the the value of gamma 0, which will be the typical Tversky loss, you have a very high loss here, right? And as you increase the gamma, your loss value is almost going to 0, and that's what perfectly you want, right? Because you want to emphasize or go towards those classes which are difficult to predict and make the loss function as 0. So that is what you see over here. Okay, so this is a quick demo, play with it and let me know your feedback. If you want some improvements on this, we can discuss and update this demo. So I'll give this demo in the X site, which you can play with. Okay, so with that, I think let's stop the discussion on the loss part, and we will go to the model part, which is exciting.